Hello, programmers! Today I'm going to talk about different sorting algorithms that we can use. I'll start with an insertion sort. My array is just 6 numbers and I want to look at how I can sort them. If I run this, I'm going to start out printing with my for loop all the numbers in the unsorted list, and then after I run my insertion sort, I'll have all of those numbers in the correct numerical order from smallest to largest. So let's look at this insertion sort. This insertion sort takes 3 input arguments: our sorted array, our unsorted array, and our size of the arrays. When you're passing in an array of anything, you're passing a pointer to the function, so you're able to make changes. So in the beginning, our sorted list has absolutely nothing filled in, but by the end, all of those values will be filled in. The size in this case is just going to be the size of 6 items, but if you want to change the size and try this algorithm out with a different sized array, we can just update that size variable in the pound define. So I'll talk through the insertion sort code and then we'll try to analyze the performance of this algorithm. I need some variables for counters. I'm going to keep track of how many of the items in the sorted array are filled in. At the beginning, we don't have anything that has a valid value in this sorted array. We'll go through in this case, 6 different items in our unsorted array, and we'll store items into this element variable. So the first time through this list, we'll put 6 there in that element. Inserted, true or false. So if you use a bool, you could put true or false, but if you're just stuck with integers, you can say 0 is false. We haven't inserted it yet. And then we're going to go through a for loop that goes from 0 to the size of the sorted array. The first time through the loop, our sorted array has absolutely nothing in it, so we're not even going to do this for loop, and we'll jump down to the if statement, say if it hasn't been inserted. Well, it hasn't. We have the inserted set to 0 or false, so we'll go ahead and update the very first item in our sorted array and set that to a 6. And then we update our sorted size by 1. So now we go through the loop again. Then this time the element is going to be set to 2, and we're going to reset inserted to 0. This time we will go through the for loop because our sorted size is 1, so we're going to go through this for loop exactly once, and we'll see that the element 2 is actually less than sorted I. I starts out at 0, so we're comparing the 6 and the 2. 2 is smaller, so we need to reorganize this array. We'll go through this for loop, so we'll set j equal to the sorted size. Right now it's just 1. Is 1 greater than I, which is in this case 0? It is, so we'll go ahead and say sorted position j is going to get sorted position j minus 1. But don't worry, we have that saved so that the 2 can go in the old place where 6 was. We have updated, we have put that inserted the element in its correct position, so we can go ahead and update the size by 1. And break will take us out of the for loop. Inserted has already been done, so we don't need to use this if statement. We're going to go back up to the top. This time the u is going to be set to 2, and we're going to set the element to 10. We'll look, and is 10 less than 6? It's not. Is it less than 2? It's not. The 10 is in the right relative spot so far, so we're not going to end up putting that in an earlier part in the array. We'll get through, and inserted will be false, so we'll go ahead and add it to our end of our sorted array, but it won't stay there forever. All right, the next time through our loop, the u is set to 3, and that means our element is whatever is in index 3, which is 7. We'll set inserted back to 0, and then we're going to start at the beginning and go from 0 to the sorted size, which is 3. If our element of 7 is less than, and we'll start looking at, is the 7 less than 2? It is not. So we'll add 1 to I. Is the element less than the 6? It's not. So we'll add 1 to I. Is the element less than 10? It definitely is. So we're going to go inside this for loop, and we're going to go start j at sorted size, which is 3. and that way we can fill in the next element of the array and copy that 10 over top of it. So temporarily we've got 2 10s until we jump out of the for loop, because we're in the position now where when we subtract 1 from j, j is no longer greater than I. So we're going to set the sorted I, which was set to 2, and we're going to set that equal to our new element, which is 7. Inserted set to 1, sorted size will add 1. We've now got 4 sorted elements in our array. No need to do that if statement. We'll go through the loop again. This time our U is set to 4, and we've got an element that is 1. And lots is going to happen here because 1 is smaller than anything else we've got so far. So we set our inserted to 0, we go through the for loop, and we look, is 1 less than the very first thing inside of our sorted array, which right now is a 2, and it most definitely is. So then we're going to go through this for loop and start with j starting at the end of our array. So j is set to the sorted size, which is 4, and we're going to go ahead and copy in position 4, which really doesn't have anything in yet, put a 10 in there. So temporarily we've got 2 10s, but we go through the for loop again, and now we're going to copy over top of that 10 in position 3. We're going to put the 7 there. The next time through the loop, then we're going to move our 6 1 over. The next time through the loop, we're going to move the 2 1 over, and then finally we're going to exit that loop and put 1 in its very first position in that sorted array. Mark that we've inserted something, add 1, and break. 5 is not as exciting. It moves around a little bit. We'll move it into its proper position in the array. So there's still some shifting going on, and then finally we're going to be done with our insertion sort. So going line by line is a great way to learn the algorithms and keeping track of what's in every variable at every time, but it makes for a pretty boring video. So I'm going to move more to the high level. One of the weak points of that last sort algorithm, that insertion sort, is that we're wasting memory. So in C, you're either dynamically allocating memory, or at the beginning of the program, you're hard coding the value that's the size of the array. So in our example, we had hard coded, we've got a size 6 for our unsorted array and a size 6 for our sorted array. And at any point in time, you could have just one array that has a sorted section and an unsorted section and use half the space. So it's not a big deal when you only have 6 numbers, but what if you've got thousands or millions of numbers? Then maybe that wasted space is going to be something you want to improve on. So the slightly better insertion sort is an in-place insertion sort, where you can start at position 0 and say, whatever's in position 0, I'm just going to say that's my sorted portion of this array, and everything to the right is unsorted. And then you're going to move on to the next position. Well, let me look at 2, compare it with the item to the left. If 2 is smaller than the item on the left, then we're going to switch places. And if you're not in position 1, you might have a trickle down effect. So in this case, I'm going to move that 2, switch places with the 6, and we move on and we look at the 10. What's to the left of it? 6 is not smaller than 10, so we don't have anything to shift around yet. We'll move over and look at the 7. Is 7 less than 10? It is, so we're going to switch places. We'll check, is the 7 less than 6? But it's not, so we know that we're done. Move on and look at the 1. It is less than 10, so it swaps places with the 10, 7, 6, 2, and it moves all the way to the beginning of that array. We'll go over to the 5, and then it'll be smaller than the 10, 7, and the 6, and it'll move into its proper position. So this is a slightly better sorting algorithm, but there are still better algorithms out there. Let me talk about one other sorting algorithm called bubble sort. It's easy conceptually, it's easy to program, but it has a pretty bad performance compared to some of the other sort algorithms. Start with the numbers in position 0 and 1, and 6 is bigger than 2, so we're going to swap those. And our array looks like something like this now. Now we'll look at the next 2 positions, 1 and 2. We don't need to swap those. 2 and 3. We need to swap those, so the 7 and the 10 will switch places. Then we'll look at the next 2 positions. and the next two positions. And so your array is a little bit more sorted. The only thing you know at the end of all of those switches is that whatever is in the very last position is in its final sorted position. So it's kind of bubbled up to the end. And if we keep going with this process, and then we're going to end up the next iteration, we'll know that our 7 is in the right position. And we try the next iteration through this algorithm, we've got the 6 in its correct sorted position. The next time through, we're going to look and we're going to end up switching the 1 and the 2 and the 2 and the 5. C doesn't have any built-in graphing capabilities unless you use other libraries. I actually implemented everything in Python and wanted to show you a graph of the bubble sort compared with the insertion sort, and then a sort I haven't even talked about yet called the merge sort. As the number of items in your array gets larger and larger, then you're going to notice that the bubble sort and the insertion sort are taking longer and longer. There are much better sorting algorithms out there, and you'll learn those later on in your data structures course. That's enough for this video. In the future, we're going to compare these sorting algorithms using something called Big O notation.